Hello, I'm going to give a presentation today on our work on extending MAPE-K to support human-machine teaming. My name is Jane Cleland-Huang. I'm from the University of Notre Dame, and I'm giving this presentation on behalf of my collaborators at Notre Dame and Johannes Kepler University. So drones are used in many different forms of emergency response scenario today. Here you can see an example of a field demo that we conducted with the city of South Bend with the firefighters to show how UAVs could support them in actions, for example, river rescue. And we're seeing an increasingly large number of applications in which multiple humans and multiple UAVs need to collaborate more closely in order to enact specific tasks. So here is a picture that was taken by drones during the fire of Notre Dame Cathedral in Paris. And this is an example in which drones really helped in the emergency response scenario, but they really served the purpose of a tool. So humans used them as a tool to get a better bird's eye view of what was going on. And the vision that we have for humans and drones goes beyond this. So in a rather dramatic picture, you can see the firefighter is going in to fight the fire, and he's partnered by intelligent, autonomous UAVs. So this brings us to the difference between traditional human on-the-loop and what we envision of human-machine partnerships. In human on-the-loop metaphor, the machine is performing its tasks autonomously, and the human is supervising the machine and intervening when necessary. But our vision is for something beyond that, for human-machine partnerships, which is sometimes referred to as human-machine teaming. And the difference between human-machine partnerships and human on-the-loop is that in the partnership metaphor, we have partnerships between two equal but different types of autonomous agents. And this is why we believe this fits into MAPE-K. MAPE-K is all about autonomy, and in this partnership, we have full autonomy between humans and machines. So thinking about this led us to look at some of the literature about human-machine teaming, and it turns out that there are three factors that are important in order to have this kind of successful teaming. The first is transparency, and the human needs to have observability into what the machine is doing, and there needs to also be predictability about what it's going to do next. Now, as we started thinking about these partnerships, we've not only thought about it from the perspective of what the human needs, but we've also started looking at it from the perspective of what the machine needs. So the machine also needs to be able to predict what the human is doing and can do. And we're going to take a look at this in a minute. As well as transparency, another factor is augmented cognition. So this means that attention needs to be able to be directed towards tasks that the machine and possibly the human needs to do. So again, it goes in both directions. They both need the ability to explore the solution space, and the machine and also the human, but especially the machine, needs the ability to adapt. So self-adaptation, which is exactly what MAPE-K is particularly strong at. And finally, coordination. Coordination involves three factors of directability, being asked to do something or directed to do it, calibrated trust between the autonomous agents, and sharing a common ground so that both types of agents can fully understand what is currently happening and will be happening in the mission. So I'm going to very quickly provide a quick overview of our own drone response platform, because I'm going to give examples and talk about how we've thought about integrating this kind of partnership into MAPE-K within the context of our own drone response system. So first of all, it's a multi-UAV system. Each of the UAVs has onboard compute capability in the form of a Jetson NX, and the behavior of each of the drones is primarily determined by its onboard state machine, which is generated dynamically. Inside any of those individual states, there are varying degrees of autonomy and decision-making about what's going to happen during that state and when transitions from one state to another are going to occur. The drone is also supported by runtime monitoring and constraint checking, and intelligence on the drone is supported by computer vision using deep learning models and on analytics. The human can interact directly with the drone. More often than not, the human or humans are going to interact through the UI, and they're going to use the affordances of the UI to generate mission requests and other information that goes through our ground control station to the onboard compute capability to communicate with the drone. Our ground control station is basically based around an MQTT message broker, and it's supported by a diverse set of microservices, which I'll talk about in a minute. So the next question is how are missions configured? And very briefly, we specify every individual specification for a drone during its mission goes through a number of common states, for example, on ground and inactive, pre-flight checks, and so on. And then the mission ends in the same way normally, returning home, landing, disarming, etc. And in the middle are the mission tasks. Now, obviously, there are fail-safe mechanisms which can allow the drone to jump from any one of these states into a fail-safe mechanism, but we're going to focus on the common path right now. So, individual drone assignments are going to take place in this part in the middle. So, one example here is search and tracking. Another is flying to a destination to deliver a device. And a third one is surveillance, hovering, and streaming video. So you can see that overall, each of the drones is going to be given one of these individual specifications, and this specification is going to be used to configure the onboard state machine. It is also supported by a specific set of microservices, for example, the mission parser, which takes the mission specification, breaks it out, and assigns specific specifications to each drone. A coordination handler, which handles communication and things between the drones, and other microservices such as airspace leasing. So that's the current situation we have with drone response today. As we started to look at human-drone interactions, we saw that there are 4 different types. Human to drone, where the human could establish mission goals. Drone to human, for example, where the drone might be reporting its state, providing explanations of its autonomous behavior, these kind of things. And then we have human-to-human collaboration, which is not the topic of today's talk, and drone-to-drone collaboration, which right now is primarily supported through coordination handlers on our ground control station, but could also be supported directly between drones in the air. So, in order to integrate human-machine teaming into our system, we started to take a deeper look at MAPE-K. We didn't deliberately initially build our system around MAPE-K. However, we did find that many principles and many aspects of MAPE-K are actually implemented within our system. So MAPE-K is a feedback control system, and the whole idea of that is with the intention to remove humans from the loop. But here we are trying to put humans back into the loop, and I'm going to talk about that in a minute. MAPE-K supports monitoring, analyzing, planning, and executing. So in this example on the right-hand side, if this UAV, this drone, were operating in an entirely autonomous mode, it starts to monitor the environment, it collects imagery, it analyzes that using its computer vision model, it determines that there's a 43% chance that this object here is in fact the person that it is searching for. It then plans corresponding actions and adaptations, and then finally executes them. So it now has the option to invite the human to help with this decision making. The human can then confirm, reject, or request the drone to circle around, to position itself better, and to get more imagery. So this is an example in which the drone could have the ability to engage the human in the decision-making process. Here is the standard MAPE-K loop. You can see the machine is doing standard things such as collecting data, analyzing the data, making some plans, and then ultimately executing them. And one of the things that we observe here is this all operates on a very fast cadence according to the ordering of the MAPE-K loop. So now let's add the human in. At the monitoring level, the human can do lots of different things. For example, the human can complement the sensor data with their own observations. For example, the drone may not be connected to Twitter, and the user may have seen some Twitter messages saying that the person who fell into the river was wearing a red jacket. So these are kind of information that the human as a monitor can contribute to the mission. At the analyzing level, the human can inspect warnings and recommendations, analyze safety and quality constraints, check for mission progress, and contribute to the analysis in many different ways. At the planning level, the human may want to, for example, change the goals or change weightings on the goals. So you could have a goal model that's being used by both the machine and by the human, and each one of them could contribute to the planning in different ways. And we're going to look at some specific examples of this in a minute. And finally, at the execution level, humans can actually physically engage in the mission. For example, the drone might be responsible for finding the missing person and for delivering a defibrillator or a flotation device, whereas the person might, or the people, may be responsible for enacting the actual rescue. One of the things that becomes obvious as you start to look at the MAPE-K cycle is that the human decision-making loop and analysis loop has a much slower cadence. And one of the challenges we have now is if we want the humans and the drones to interact together within the MAPE-K loop, we have to somehow overcome these differences in cadences. Now in the middle we have a knowledge base, and I'm just going to show some of the many different kinds of runtime models that we use to start to address this, and I'm going to look at a couple of models in more detail. So MAPE-K employs diverse runtime models that represent lots of different things about the structure, behavior, and goals of the system at runtime. And one of the questions that we posed is, how can these same models at runtime support human-machine teaming? And this includes, of course, the human and the machine collaborative decision-making. So I'm going to try and answer those with respect to these three human-machine factors of transparency, augmented cognition, and coordination. So I'm going to show you a few of the different models that we've integrated into drone response. The first one really is built off the fact that each of our UAVs has a configured state machine for each mission. Each UAV could have its own unique state machine depending on the tasks that it has been assigned. So in this runtime model, what we do is we combine the different state machines into a state transition diagram, and we place markers for each drone onto the state transition diagram. So in our environment, for safety purposes, each of our drones has a name, and each of those names is a color. So we have a green, red, orange, blue, and purple drone, and our drones are all color coordinated, both in the UI and in the physical world. And what we can see from this runtime model is we achieve some degree of transparency through observability. At any time, we can see exactly which state each drone is in. But we have less support from this particular model for predictability because this is a merged model of the state transition diagram, and it's not always clear exactly which option or which next step each drone is going to take. So we've made it interactive, whereby you can ask for a view by clicking on any one of the individual drones, which only shows the state transition diagram for that particular drone. So this is an example of a view that built upon an existing runtime model of the state transitions allowed for each drone. It merges them into a kind of aggregated form, and it generates a model that is suited to the human. So the human is going to benefit from this particular transparency model. However, the robot doesn't benefit as much. The robot could, for example, see where all the other drones are, but the robot gets no transparency into the human state. In other words, it doesn't know things like how available are humans to help with tasks that it might wish to request help for. So we've found that robots need transparency too. So given our previous example, I mentioned before that our UAVs coordinate tasks through the coordination handler, and different types of tasks have different specifications. So here we can see a specification of a coordination handler that is explaining how the drone is going to request help and get interactive help from the user. And note, it says if human is available and responsive. So this suggests that we need to have new kinds of underlying runtime model that track the current behavior of the human and are aware, for example, of their workload, whether they would be available, can we ask them to do something if it's going to increase the likelihood of a successful mission or not. So this leads to the question of what help can the robot expect from the human at any particular critical decision point. So here's an example of a cognition model. Here we specify all the different kinds of alert types, and then we have a runtime model that for each view we present tracks the users that are currently interacting with that view and the number of alerts that we've placed on the screen. So this helps us to understand how much information, what is the cognitive load that we are expecting on the humans right now, and it allows the machine, in this case the system, to decide whether to display another alert, whether to reprioritize the existing alerts. Now we never hide alerts, we always show the user how many alerts are currently available, but only some of them will be prominently displayed at any one time. Here's another cognition model that we've used to generate explanations of autonomous behavior. So the user always wants and needs to know if a UAV has made a significant adaptation decision, and they may want to request more information about it with a rationale, so this model supports generating that kind of information. And then finally we have a goal model. I'm not going to discuss the goal models very much because this is a new area that we're currently integrating into drone response, but you can see here a very high level kind of goal view, which basically tracks which of these goals individual humans and individual UAVs are working towards achieving. Finally, in terms of models, I want to talk about coordination models, which I think are really crucial to the success of this human-machine partnerships. So, coordination could be initiated by the UAV, and we've already seen an example of how it could do that. It could also be initiated from the human when the human specifically changes the goals of the mission or asks a drone to perform a specific task that it thinks is important. But the third type of problem I think is more important, and that is the tug of war that occurs between UAV and human initiated actions. So coordination problems. Most people are familiar with a very sad case of the Lion Air Flight 610 crash and the corresponding crash of Ethiopian Airlines Flight 302. And what happened is that the MCAS system, which is responsible for maneuvering characteristics augmentation, it incorrectly perceived that the angle of attack, which means that the angle at which the drone was flying, was exceeding a predefined limit, and so it automatically pushed the nose down. the pilots, obviously not wanting the plane to be flying down towards the ground, pushed their nose up, and we started to have a tug of war between the pilots that didn't know that they could turn the system off and the system itself. And these are very problematic issues that we have to address in these kind of human-machine teaming examples. A similar example in our UAV space. Imagine that a UAV is tasked with collecting imagery of a riverbed. It determines the best altitude, descends close to the water in order to optimize the video. Unfortunately, the sunlight reflects from the water ripples and disturbs the sensor readings and causes a sudden fluctuation in altitude. So the drone starts dramatically going up and down. The human notices, intervenes, causes or directs the UAV to ascend to a safe altitude. The flight becomes stabilized. Control is ceded back to the UAV, which then determines that it could do better if it went to an altitude closer to the water, and the whole cycle starts again. So how do we break these cycles? We need to have runtime models that support this. So for example, models that can detect these kind of cycles and know what to do when they are observed and detected. Another challenge is that with all of these runtime models that we're introducing to support human-machine teaming, we have all sorts of different sensor readings that are needed at different periods of time. So one of the open challenges is to create a modeling environment that optimizes the reading of sensors, to try and optimize it to support human and robot coordination models. Given all of these runtime models, we've realized that we have different kinds of, we can classify them into 3 different forms. First of all, we have the GUI front-end models, which are the user-facing ones. And then at the bottom, we have the runtime models, or the models at runtime that were needed implicitly by the MAPE-K loop anyway. And then we have this new kind of model in the middle, which basically are new forms of runtime model that are needed to support human-machine teaming. And these are the models that often generate the information needed by the GUI models. Finally, to take a more holistic approach, we need, if we want to build human-machine teaming systems and integrate them into MAPE-K, we have to explicitly design for them. So this requires proactive requirements elicitation, analysis and specification, thinking very carefully about the types of runtime models that we need, designing and prototyping the user affordances and the UI components of this, and then ultimately implementing and deploying. So I'm going to conclude with 3 takeaways. First of all, to achieve human-machine partnerships in multi-UAV, multi-human scenarios, we need to integrate better support for transparency, cognition, and coordination into our MAPE-K framework. And in particular, we need to have a deeper understanding of the coordination challenges, the place at which the humans and the drones really interact. How do we better support directability, bring about calibrated trust and common ground? And finally, we need to do all of this despite the different cadences at which humans and machines operate. Thank you.